We're going to work through problem 4.10 of chapter 4 of Taylor's Classical Mechanics. This is from the section on force as a gradient of potential energy. And this is really a problem if you don't have much experience taking partial derivatives. This is a good review of that. It's not that hard. What we're going to be doing is when you take a partial derivative with respect to x of a function of x, y, and z, you're treating y and z as constants and taking a derivative as you normally would, only with respect to x. So for a, we have our function of x, y, and z. It's ax squared plus bxy plus cy squared. And the notation is going to be over del x is going to be equal to, here it's just going to be 2ax. Here with respect to x, we're just treating y as a constant, just like we're treating b, a, and c as constants. It's going to be plus by. With respect to x, x isn't even here, and these are just constants as we're treating them as such. So that's just going to be 0. So this is our partial derivative with respect to x. Now, we'll take our partial with respect to y. Same procedure. This doesn't have any y's. That's going to 0. This is just going to be bx. This is going to be 2cy. And it's just bx plus 2cy. Not so bad. Take our derivative with respect to z. No z's here. No z's here. No z's here. All constants. Derivative with respect to z is just going to be 0. For part B, the function they're giving us is g of x, y, and z is equal to the sine of ax, y, z squared. All right, so we're going to take the partial with respect to x, and this means that we're using the chain rule. Our x is inside of here, so we do have to do it. If there was no x inside of here, simply would be 0. Our x is here. We're going to take the derivative of the inside, which is going to be a y z squared with respect to x. That y z squared and the a are all constants in this case. That's how we're treating them. And then it's going to be times cosine of ax y z squared, just like you would usually take the derivative of sine. You'll notice a pattern here. Derivative with respect to y is just simply going to be ax z squared cosine of ax y z squared. And our derivative with respect to z is going to be 2axy z cosine axyz squared. If you've seen this stuff before, this may seem fairly straightforward, but it is a good review as you will use the gradient of the potential energy to model the force. So for part C, we have h of x, y, and z. And this is equal to ae to the xy over z squared. So, with respect to x, we're going to take the derivative of this top portion. With respect to x is pretty easy. Just get y over z squared times a times e to the xy over z squared. Just our normal chain rule being applied. We're just treating everything else as constants. We have, with respect to y, it's going to look very similar. X over z squared, a e to the xy over z squared. And with respect to z, keep doing that. With respect to z, we're going to have the derivative of that portion there. That's the same as xyz to the negative 2. So that's the same as saying negative 2xy over z to the third is our derivative of that, times a e to the xy over z squared. That is in the exponent, just in case that's not clear here. And I think that covers the entire problem.